All right, so we're happy to have Noah Stephens-Davidowitz today. He's a professor at Cornell University. He's very famous for his results in lattices, cryptography, and complexity. In particular, he resolved a big question called the reverse Minkowski conjecture. And today, Noah is going to talk about the new kind of cryptography, cryptography of the 21st century. Noah?
Yeah, thanks, Sasha. So yeah, today I'm going to be talking about cryptography from lattices, which is also referred to as post-quantum cryptography. You'll see why. And today, this is going to be I hope a highly non-technical talk. I'll do my best. It's really not going to be actually focused on any particular research, certainly not particular research of mine, but it's sort of loosely based on joint work by myself, Devesh, Huck, Sasha, and Vinod. So Devesh is at National University of Singapore. Huck is University of Michigan. He's on the job market right now. Sasha is Sasha, and Vinod's at MIT. And I'm at Cornell. Okay, so let's begin. So our story starts with public key encryption. Or actually, it starts with just sort of plain old boring secret key encryption. So let me tell you what secret key encryption is at a super high level. So here's me, and I wish to communicate with Gmail, with Google, and I want to send some sensitive information to Google, which is a common issue that I have. And I think the way that we imagine this when we're sort of not thinking about it carefully, we have this sort of cartoon image where there's this wire that comes out of my computer. And so I'm in Ithaca, New York right now. So the wire travels west, across, okay, I don't know my geography very well, but the Great Plains and the Rocky Mountains and stuff. And eventually it makes it to Mountain View, California. And then it plugs into some computer at Google headquarters there. And this is really convenient, right? Because this private wire that I have allows me to send information to Google without nonstop trip, right? But in reality, of course, that's not what happens, right? In reality, we send our sensitive information over the internet. And so here the internet is represented by this shady character over here, right? So the internet's full of all sorts of shady characters who would like to learn my personal information. And so if I were to send my sensitive information in the clear over the internet, that would be a bad time for me. I would be upset about this situation. So what we do instead is we use various forms of encryption. And the simplest form of encryption, which itself is quite complicated. And in my cryptography class, we're about a month in, and we just saw our first secret key encryption scheme. So this is a caricature, but the rough idea is that Google and I each share ourselves a secret key K. So we both have the same key, and you can think of this as a uniformly random string. And then say my very private, sensitive, embarrassing information is the string 0101, just for simplicity. And then the world's simplest secret key encryption scheme, the most beautiful, in my opinion, secret key encryption scheme, is just the one-time pad. So if my key is 1100 and my private message is 0101, then I can XOR the two together. So bitwise XOR. I'll get the ciphertext 1001. And then instead of sending my embarrassing information directly, I'll send this ciphertext C. And the idea is that if our keys sampled uniformly at random, then from the adversary's perspective, C is just a uniformly random string. It doesn't learn anything about what I want to say to Google. But of course, Google, having the secret key, can reverse this operation. It can just XOR again with the secret key and get back my message. So this is called the one-time pad. It's problematic in various ways, but for the purposes of this talk, this is what I mean by secret key encryption. But the big problem with this scheme is the question of where the key comes from. Right? So in order for this to work, Google and I need to share a secret key K. And very importantly, the adversary should not know it, right? So the obvious thing to do, oh, I want to share a string with Google. So, I'll send it over the internet, right? But that's circular, right? If Google and I were to use the internet, if I were to send this over the internet, then the adversary would know the scheme. So somehow we need to share this secret key. And of course, like what we do in reality is we don't do this. We use public key encryption, which I'll get to in a second. But I think it's kind of instructive, just kind of a fun thought experiment to think like, what would the world be like if we didn't have public key encryption? Like if we really relied on secret key encryption, like how would that work? And of course, like I have no idea, like, you know, the economy and civilization is like a complicated thing. Maybe we'd adapt in all sorts of weird ways, but like you can imagine maybe like you get your like secret key in the mail, right? It's like Google sends you like in the mail, like, I don't know, maybe it's like a USB drive or something that has like a bunch of uniformly random bits on it. And like you can only communicate securely with like websites that like have sent you a package in the mail. Or maybe like you go to a store and you like buy a secret key. Or like you physically walk to Google and like pick up your secret key from there. So I think it's just sort of fun to imagine. But luckily we like don't seem to live in that world. We seem to live in a world, a magical world, in my opinion, in which public key encryption exists. So I still like, when I hear the definition of public key encryption, I still think it sounds impossible. I know many, many schemes that achieve it. So it seems to me that like, actually it is possible, but it still seems like magic to me. And the way the public key encryption works is, this is a ridiculous, crazy idea, originally due to Merkle and Hellman and Diffie and Hellman in the mid 70s. The idea is, so Google still has a secret key, but I don't have a secret key. I have something else called a public key. I'll say more about that in a second. And the public key can be used with this magical encryption algorithm to convert my embarrassing personal information into a ciphertext. And then Google can use, I'll send that ciphertext to Google, and then Google can use a magical decryption algorithm together with its secret key, so not the same key that I used, in order to decrypt this and get my information back. And what's crazy about this is that the adversary can have the public key. So when I say public key, I mean public. Like literally, I mean, this actually happens. Google publishes public key on its website. Everybody knows it, including, you know, whatever sort of shady characters are trying to steal my information. And so the magic of this scheme is that even though the adversary knows the same information that I know, even though it knows the public key too, somehow the adversary shouldn't be able to read my message in a certain like very formal way that I won't get into here. So now like at this point in the talk, like I need an obligatory slide where I say that public key encryption is useful. But this is a very silly thing to do because like no matter what I do, I will damn public key encryption with faint praise, right? So like, yes, it's useful for communicating medical information. It's useful for buying things over the internet, useful for banking over the internet and Signal and sending emails, but it's the entire internet, right? The entire internet relies on public key encryption. The line that I usually say to keep myself from getting in trouble is that most internet traffic uses public key crypto in some form or another. The reality is it's very hard to get statistics on this, but sort of everything that's important that happens over the internet uses public key encryption. For example, I'm speaking to you right now and public key encryption is happening. You know, various number theoretic things are happening. All our computers are doing pointless number theory in order to secure things. And of course, the big drawback of public key encryption is that the security of any public key encryption scheme, we know a few and I'll mention them, relies on computational hardness assumptions. So for example, you might have heard that like lots of public key crypto or lots of crypto in general relies on the assumption that factoring large numbers is computationally difficult. And this is just an assumption, right? So like we as a species, like we're not that bright, like we're not really able to prove computational hardness of anything, Sasha being a rare exception. Instead, we just sort of assume. We think it's hard to factor large numbers, and if we're wrong about that, then public key crypto goes away, or at least some forms of public key crypto go away. So like, I think public key crypto is magic. Every time I hear the definition, I get a little skeptical because of this idea that like somehow the adversary knows everything I know. So like, how should I be able to do anything that the adversary can't like sort of undo? And like evidence against my skepticism is that we seem to have schemes that are secure. But like, my skepticism at least suggests that there shouldn't be that many ways to do public key encryption. Like it's this very magical, crazy thing. So like, it's not like we have a ton of options, and we don't. So the two main options are what are known as factoring-based constructions and discrete log-based constructions. And here we categorize them more or less by like the computational hardness assumption that's necessary for security. Again, everything I'm saying in this talk is hand-wavy. Like for example, the RSA crypto scheme, which you've probably heard of due to Ravesh, Shabir, and Edelman. In that scheme, your public key is the product of two primes, p times q, and your secret key is the two primes themselves, p and q. So we say this like a factoring based scheme because like clearly if you can factor pq efficiently, p times q efficiently, then you can break this scheme. Like without even telling you anything else about the scheme, it's clear that if you can factor, then you can break the scheme, because if you can factor, then you can get the secret key given the public key, and the secret key is enough to decrypt my message by definition. Another class of schemes are called discrete log based. And these are like mathematically like slightly more difficult, but for those in the audience who know what I mean, these are based on groups. So you have some group element G, and the public key is G raised to some power X, and the secret key is that power X. And so we say that these are discrete log based because we call finding X given G to the X the discrete logarithm problem. The canonical example of this is a Diffie-Hellman key agreement. It was actually the original encryption scheme, although kind of at the time, Diffie and Hellman didn't realize it was the original encryption scheme. Oh, and I apologize for this silly typo on the slide. That's not how you spell Hellman. What did I want to say? It turns out that like this is what we use. So nearly all secure communication uses this, and like most internet traffic, but really, I mean, essentially all interesting internet traffic relies on one of these two ideas. In fact, almost all of it relies on discrete log-based constructions because we know how to do those more efficiently. So like all our eggs are kind of in one basket. We do have other things as well. So you might remember that the talk is called Lattice-Based Crypto, so I should probably mention it. There are what are known as lattice-based constructions, and these, ignoring some history and possibly angering some people, like the first real lattice-based crypto scheme was due to my advisor, Oded Regev. He recently won the Gödel Prize, or now it was like 3 years ago or something, for this. And I'm going to have a lot more to say about that in a bit. And to like avoid angering people too much, I'll sort of mention briefly that there do exist other ways that we know how to build public key crypto that I'm just sort of going to ignore for the purposes of this talk. These are by far the three best studied. There's also code-based crypto, which is very similar to lattices, and then there are sort of more exotic constructions. But sort of the starting point for this talk, or sort of like the reason I want everyone to panic, is because of the following horrible coincidence, and I really do think of it as a coincidence. So remember, we have these factoring and discrete log-based schemes. They're secure only if factoring and discrete log happen to be hard. For classical computers, as far as we know, these are hard problems, and like people seem to really believe that conjecture. I think I probably believe it too. But for quantum computers, we know that they're not hard. So if you can build like a reasonably sized quantum computer, where reasonably sized means much bigger than what we can do now, then you can factor the sort of numbers that we use currently to secure internet communication. You can also compute discrete logarithms. It turns out that even though these are two different problems, they're kind of closely related in ways that maybe we don't really understand. So sort of every time we come up with an algorithm for one, we come up with an algorithm for the other, it seems. So this goes all the way back to Peter Shor in the mid-90s. So we've known this for a really long time. But it's gotten, like, it was this sort of interesting curiosity in the mid-90s, very interesting curiosity, but it's gotten more and more scary as progress in quantum computing has increased. I'm not an expert on quantum computing. Certainly, I'm not an expert on actually implementing quantum computers, but people who are very nervous about this. In fact, the National Security Agency, so like, you know, very serious like spy organization, announced all the way back in 2015 now that they wanted to initiate a transition to quantum resistant algorithms in the not too distant future. It's unfortunate that this quote is sort of difficult to parse. What they were saying is, we don't want to use this kind of crypto anymore because it's not secure. against quantum computers, and we're worried that quantum computers will be built. And they said this again all the way back in 2015. And when they say quantum resistant algorithms, or what people now call post-quantum cryptography, what they mean is lattice-based crypto. Because lattice-based crypto is like, well, it's not one of these two things that are known to be broken. And it's by far the best studied of the things that aren't those two things. And I just want to like pause and say here that like, when I talk about lattice crypto being post-quantum, like I often get the question, why is lattice crypto post-quantum? Which is a very fair question, but I think it turns out to actually be the wrong question. I think the interesting question is, why aren't these secure against quantum computers? Why isn't factoring discrete logarithms secure against quantum computers? Because like, okay, I'm not an expert on quantum computing, but like, you know, I've been around, and like, I only really know like 3 problems that quantum computers can solve exponentially faster than classical computers. One is simulating quantum systems, which sounds trivial, but it actually is like the killer application of quantum computers and is really incredibly interesting. And the other 2 are factoring and discrete logarithm, right? So like somehow quantum computers, they're very, very specific things that are very, very good at a few computational tasks. And for some very strange reason, 2 of the 3 that I know of are sort of negative applications, right? Nobody wants to factor big integers. Like, okay, it comes up occasionally, but for the most part, like the main reason anyone want to factor big integers is to do something evil, right? And like read your messages or something like this. So it's like, we just wish it were hard, but somehow for quantum computers, it's not. And what a strange coincidence. So like the fact that lattices seem to be secure against quantum computers, which means that we don't seem to know any algorithms that break these things quantumly, is not the surprising fact. The surprising fact is that we happen to know, you know, that Shor found these amazing algorithms for factoring discrete log. It's really just one algorithm. Okay, so tangent aside, I should say like there's actually like this real rush to do this. So like, I mean, you can see this already because like I'm showing you a quote from 2015 where the NSA is saying this. Oh, and I should say the NSA said this in the context of like, one of the NSA's jobs is to decide what crypto the US government uses. So like, I guess it was in that role that the NSA was saying we should switch to quantum algorithms. They mean like, you know, to secure like, I don't know, the nuclear codes or something like this, we should probably not be using things that are broken by quantum computers. So first of all, yeah, like we've been talking about this for at least, you know, 6 years now, in fact, longer. But the other reason that we're really late is because in practice, like, it's not okay to just be secure against the adversaries that exist right now, right? So like, as far as we know, nobody has a large quantum computer right now that can factor numbers. Like, I think the record is someone factored 21 with a quantum computer. It turns out to be 7 times 3, but like, that's not big enough. Like, suppose 5 years from now, someone builds a quantum computer that's big enough to factor numbers. That would be a huge disaster, right? Because that would mean that all the messages that are being sent securely today, and in fact, for the past like 5-10 years or so, that are being stored in these huge data centers by, you know, various spy agencies, the NSA included. But, you know, if you're a fan of the NSA, then like, you know, pick your favorite large country or pick your least favorite large country. They're doing it too, right? Everyone's scooping up huge amounts of internet traffic with the intention of decrypting it in the future if they can. Right? We now know that this is happening. In fact, this is part of the Edward Snowden leaks. So your crypto shouldn't just be secure against today's algorithms. It has to be secure against future algorithms as well. And like, you know, I'm not a practitioner. I'm not a security person, even though I'm kind of playing one a little bit for this talk. But the time horizon that I often hear people quote is 40 years, which seems about reasonable to me. You know, if someone can read my private messages 40 years from now, like, okay, fine, maybe I don't mind that. But 5 years from now, it doesn't sound great. And, you know, I'm not a political dissident. So like, we really should have done this before people started scooping up all this internet traffic. So we're way, way late to the game here. Okay, so disaster, we're in a lot of trouble. Let's see how to solve the problem. And we're going to solve the problem using lattices, right? So let me tell you what a lattice is. We're going to sort of step back. So a lattice, well, they're beautiful objects. I spend my whole life thinking about them. They're a discrete set of vectors in n-dimensional space. Here is a lattice in 2 dimensions. So an important thing when I give these talks is like, So I'm sort of not particularly able. So like I draw things in 2 dimensions. But you should be picturing things in 500 or 1,000 dimensions. So I'll trust you to do so. So here's a 2-dimensional lattice. It's a discrete set of vectors in n-dimensional space. You can see it has this sort of nice periodic nature. It's specified by a basis, B1 through Bn, of linearly independent vectors. So here's a basis for this lattice. And the lattice itself is the set of all integer linear combinations of the basis vectors. So in other words, an integer times b1 plus an integer times b2 plus an integer times b3. I should mention, because sometimes it's confusing, like negative integers are allowed too. So for example, this is a lattice point, the point I have circled here. Why is it a lattice point? Well, it's a lattice point because it is 2b1 plus b2. 2 and 1 are integers, so this is a lattice point. And something that's not immediately obvious about lattices, I think maybe you're smarter than me, maybe it's obvious to you, that is that the lattice basis is not unique. So I gave you 2 basis vectors that generate this lattice, but here's another basis that also generates this lattice. And I tried to choose these vectors, I'm not sure how well I did, so that you can kind of tell that actually they do generate the same lattice just by checking, like, notice that it suffices to check that my original basis, b1, b2, can be written as integer linear combinations of these guys. And maybe you can see, like, for example, b1 is just the difference of these 2 vectors, and b2 takes a little bit more work, but you'll see that also it is an integer linear combination of my vectors here. And there's actually like a notion, for the purposes of this talk, a rather vague notion of good bases versus bad bases. And like, the most high level idea is that a good basis should consist of short vectors and a bad basis consists of long vectors. So for example, like the basis b1, b2 that I showed you, like if I just gave you those 2 vectors and didn't show you this whole nice picture, you would be able to roughly tell like what the lattice looks like. But if I give you these 2 long vectors, it's a lot less clear what the lattice looks like. And of course, you know, picture n vectors in very high dimensions and it becomes less clear. Hopefully. And in fact, it's computationally difficult if I give you a long basis, a bad basis for a lattice. It's computationally difficult to find a good basis, a short basis. And I'm going to say more about that in a bit. So let's see how to use this to do crypto, public key crypto. And this scheme is a caricature. It doesn't actually satisfy like a good notion of security, but I really like it because actually, like in my opinion, it's by far the simplest caricature of a public key encryption scheme that I can give you. Like RSA, I can't explain to like a person on the street. This, I feel like, you know, if it were a particularly committed person on the street, I could probably get it across. So here's the idea. My secret key is going to be a good basis for a lattice. So some short vectors that generate a lattice. And like, you know, I get these somehow, like I sample them randomly in some clever way. Don't worry about the details. So that's Google's secret key. The public key is a bad basis for a lattice. You can see that this particular basis is so bad that it like doesn't even fit, right? These are very long vectors. I had to shrink them in order to get them into my little box here. So it's a very bad basis for a lattice. Now to use this as an encryption scheme, I'm going to encode my sensitive information as a lattice point, right? And this is not hard to do. Like, what is a lattice point? Well, given a basis, like my bad basis, the public key here, it's just a list of integers. It's the integer coordinates. So like, you know, pick your favorite encoding scheme from like emails to list of integers. Everything's a list of integers anyway, right? But I don't send that, right? If I were to send this point in the clear to Google, then anyone with the public key could like do a little linear algebra and they could figure out like what the coordinates of that point were in the public key and they would know what message I sent, right? So that's not good. What I send instead is a noisy version of the message. So in other words, I add a little bit of error, a little bit of noise to my message. And now instead of having a lattice point, so a point with integer coordinates, I have some point in space that doesn't have integer coordinates in my basis anymore. And of course, like what's cool about this is anyone with the public key can do this. Anyone with a public key can encode their point as their message as a lattice vector and add a little bit of noise to it in real space. But Gmail can actually decode using the secret key. And like there are fancy ways to decode, but here's like a not fancy way. The not fancy way is to take the secret key to express this noisy message, the ciphertext, in terms of the secret key. So as a linear combination of the secret key vectors, it won't be integer coordinates because it's not a lattice point, right? But if my vectors are short enough and like nice and orthogonal, and if my message didn't add too much noise, if I didn't add too much noise to my message, then the coordinates will be very close to integers because I didn't add that much noise. And if, in particular, if I just round the coordinates, then I'll get back to the original point. So Google can decode just by linear algebra plus rounding. And we think, as far as we know, that an adversary would need exponential time to decode this message. Where here exponential means exponential in the dimension of the lattice. So in 2 dimensions, this is not secure. And in fact, the way I describe this scheme, it's not secure in any dimensions, but modified slightly, it is in fact secure. And we think that an appropriate modification of this scheme takes exponential time to decode. So it's like very simple, you know, like I have some way of decoding noise that other people don't have, and I use that to build public key encryption. That's the idea. And this turns out to be really useful for lots of reasons. So like one reason is that you can do lots of cryptographic tasks besides just public key encryption. So I think public key encryption is magic. I'm satisfied. But there are other things like fully homomorphic encryption, which you might have heard, functional encryption, homomorphic signatures, identity-based encryption, attribute-based encryption, all sorts of exotic cryptographic primitives that, you know, keep cryptographers off the streets that are known how to be done with lattice-based crypto, many of which are not known how to be done in any other way. So lattice-based crypto turns out to be extremely expressive. It's also extremely well studied, maybe not as well studied as factoring, but quite well studied. And I'm going to talk a ton about that later. So let's not say anything else about it now. And as far as we know, it's secure against quantum computers. And again, like I think of this more as a statement about factoring in discrete log than about lattices. Like it just doesn't happen to have the strange, unfortunate problem that factoring in discrete log have, as best as we can tell. And most importantly, this is going to be used by a lot of people. Like the internet, in the not too distant future. In fact, like there's this whole complicated bureaucratic process run by NIST, the National Institute for Standards and Technology, which is a US government agency that standardizes things. And they're kind of the de facto people who decide what cryptography gets used for the internet. You know, it's not their official role, but it's what happens in practice. And here's some very long text that NIST writes. It's very bureaucratic, but they're saying that they've started a competition where different people propose different variants of essentially the scheme that I showed you on the previous slide that will effectively be used to replace factoring and discrete log-based crypto to run the internet on. So we're really doing this, and just because it's fun, I'll show you some of the logos of some of the schemes. They have fun names like Crystals and Falcon and Frodo and A New Hope and Tesla or Q Tesla. And if like you don't like the public sector, the private sector is involved too. So this is actually a very old article at this point, back from 2016. You can already use lattice-based crypto in your Chrome browser if you want. Or in the Canary version of the Chrome browser, which is the beta version. And that's been around since 2016. The point being that lattice crypto is coming. In fact, like I try not to get hung up too much in the bureaucracy, but like we're in the final stages of this standardization process. We're in what they're calling round 3 of a 3-round process. And so they say, well, like within like a year or so, they'll be done. And then God knows how long it will take to like sort of percolate to the rest of the internet. But we're trying to do this. So it seems worth, I think, studying the computational problem that underlies the security of these schemes. And that problem is called the shortest vector problem, or SVP. And sometimes it comes with a little parameter, gamma, which I'll describe in a second. So the shortest vector problem, you're given as input a lattice, which means you're given as input a basis. Think of like a bad basis. So you're given like a bunch of vectors in space that like all point in roughly the same direction. And by some definition, they're very long. And your goal is to find the shortest non-zero vector in the lattice. So in other words, your goal is to find a non-zero integer linear combination of these vectors that's short. That's the exact problem. The approximate problem is to find an approximate shortest vector. So there's this parameter gamma, and you're willing to be off, but you're allowed to be off by a factor of gamma in the length of the vector. So the details are like tremendously unimportant for this talk. In fact, you might notice that like I kind of, so these are the two problems, SVP and gamma SVP, where gamma is an approximation factor. You'll notice that like I put a little switcheroo, like in the scheme that I showed you, it seems like what you need is a short basis for a lattice. And now I'm talking about short vectors. And also like, I have not defined what short means, and like, you should have absolutely no idea like what a reasonable approximation factor might be here, or if this is even the right definition. It turns out it is. But for the purpose of this talk, you don't need to know the details. The important thing is that this problem is called SVP. It corresponds to finding short vectors in a lattice. And there's this parameter gamma. And as gamma gets larger, the vectors get less short. So they become less useful. And eventually they're not useful for decrypting. They're not useful for breaking the scheme anymore. But of course, as gamma gets larger, the problem, at least theoretically, becomes easier. And in fact, in practice, it becomes easier too. We know this. Okay. This is a well-studied problem. This slide is meant to scare you. Please don't try to look at it. This is, and I know like, you know, there are experts in the audience who are like very offended that I left out their favorite paper here. This is an incomplete description of a list of some of the more interesting research, in my opinion, on this problem. But the point of this slide is just to say that like we studied this problem a lot, and that this problem is interesting for like a really wide range of approximation factors gamma. So from your perspective, like what a reasonable approximation factor is like makes no sense at all. Like you shouldn't know that like root n turns out to be interesting, but it turns out it does. Gamma equals root n is an interesting approximation factor. But like we've studied this this problem in a tremendous number of different regimes, and in different regimes we know different things about it. Like oops, I meant to how do I do this? Zoom in. For example, we know NP hardness in some regimes. In other regimes, we know other forms of hardness. In other regimes, we know that the problem's easy, it's in P, and everything in between. So pick your favorite complexity class. There's some approximation factor where SVP is relevant. This is one of the reasons I love this problem. So super well studied, very interesting in my opinion. And as I kind of already said, the fastest known algorithms for this problem run in time exponential in n. For the approximation factors that are relevant in this talk. It turns out that for some reason, and it's not obvious at all, the approximation factors that are relevant for crypto are polynomial in the dimension n, but it's really not obvious why that should be true. Turns out to be true. Okay. So let me now tell you what evidence we have that lattice-based crypto actually is secure. So these are like the pros of lattice-based crypto. And let me temper your expectations by saying that we don't know how to prove security of anything, right? So I'm not going to unconditionally prove the security of a crypto scheme for you today. I'm not going to tell you that someone else has done so either. And that's because like, okay, modulo some technical details, like that's much stronger than proving that P doesn't equal NP, right? And we don't know how to prove that. Like we as a species do not know how to do this stuff except for Sasha. And so we therefore, I'm not going to show you very strong evidence, but I'm going to show you what evidence we have. And relative to the competition, the evidence is actually pretty good. So here's the first piece of evidence. It's that nobody's broken lattice-based crypto yet, and some number of people have tried to do so. So the standard party line is to say nobody's broken lattice-based crypto yet, and many people have tried. I'm a little uncomfortable with that statement. Like this is where I work all day. Like I kind of know most of the people who work on this problem, and calling it many is maybe a little. I mean, there are enough of us to have a workshop. Right, so that's nice, but it's not as well studied as factoring. But this is probably the strongest piece of evidence. It's also the one that is least interesting to talk about. But I should say, like, I'd be remiss if I didn't mention this. People have tried, and if I were talking about RSA or Diffie-Hellman, then the talk would stop now, and you guys could ask me questions. I mean, you could ask me questions anyway, but like I'd be done speaking. Because like for other schemes, this is all we know. For factoring, like there's no sort of or very, very little sort of concrete evidence that factoring is hard. We just know that we haven't broken it. For lattices, I can keep going. In fact, I can say a lot more than I will. To give you more evidence, let's just sort of remember sort of like one of the few tools that we have as theorists to study such things, which is known as the reduction, right? We say that problem A reduces to problem B if we can solve A efficiently given a solution to B, right? It's always hard to get the directions right in these things, but the idea is like, if it turns out that B was easy, then A was easy. In other words, I can convert an instance of problem A into an instance of problem B, such that if you solve the instance of problem B, then you've solved A. Okay. And just to make it more confusing, theorists, we always take the contrapositive of this, right? Like, we're almost never interested in the actual, if B is easy, then A is easy. We're almost always interested in if A is hard, then B is hard, which is just a contrapositive of this. And so because we can't prove security, we use reductions to prove conditional security. We say, well, okay, we don't know if either of these problems is hard, but we know that B is at least as hard as A, which is, you know, a start. There are many, many reductions between gamma SVP and lattice crypto that go in all sorts of fun directions. So we've already seen one that's kind of trivial. So in order to break lattice crypto, it suffices to solve SVP, right? So like the public key to a lattice-based crypto scheme is a bad basis. SVP allows you to find a good basis. So if you want to break lattice crypto, it suffices to solve SVP. This is true. There's in fact another reduction that's relevant here, which is that if you want to solve approximate SVP, which is enough to break lattice crypto, it turns out that it's enough to solve exact SVP, which actually sounds really silly. Like, of course, if you want to solve the approximate problem, it's enough to solve the exact problem. But this is actually a highly non-trivial reduction because it reduces approximate SVP in large dimensions to exact SVP in lower dimensions. And this is like a technical point, but I actually think it's very philosophically interesting. And I'll come back to it. But just as a reminder, our best algorithms for the relevant problems when parameterized appropriately run in exponential time. Okay, so these are sort of the reductions in terms of how we break lattice crypto. But it turns out that we have reduction in the other direction. So we can reduce approximate SVP to breaking lattice crypto. And this is actually very surprising because like the way that lattice crypto works, right? I have to like come up with a secret key somehow. I have to like generate a specific lattice, which is going to involve some randomness. It's going to involve flipping some coins. And like, so clearly lattice crypto is like equivalent to like breaking some kind of problem on that explicit lattice. But what this reduction says is that if you can break lattice crypto, then you can find short vectors in any lattice. So there's like this common issue that comes up, for example, with RSA, where like maybe it's hard to factor integers, but is it hard to factor your integers? Is it hard to factor the integers that you chose for your RSA public key? And with RSA, you know, it's not exactly clear. And in fact, like over the years, guidance has changed on how to choose your public key as new factoring algorithms have been developed that haven't necessarily broken factoring in general, but they have made factoring a lot easier on some public keys. And somehow for lattices, we kind of know that that's not an issue because we kind of know that if you can break lattice crypto, sort of as Oded defined it, and as it's actually used, then you can find short vectors in any lattice. So the lattices that we choose are in some sense the hardest lattices possible. And this is known as a worst case to average case reduction because it reduces the worst case of finding a short vector in any lattice to the average case of finding a short vector in the lattice that I sampled for my public key. Let's put this together. So we have this sort of complicated chain of reductions, reducing various forms of SVP to each other through lattice crypto. And if you squint, then you'll see that breaking lattice crypto is essentially equivalent to solving approximate SVP, but only if you squint. The issue is that there are these specific approximation factors. So there's this one that I'm calling gamma sec over here. And gamma sec for security is the approximation factor that we know can be reduced to solving lattice crypto. So lattice crypto is no easier than solving gamma sec SVP. but the approximation factor that we need to break lattice crypto is smaller. So if you don't care about the approximation factor, then you can say lattice crypto is equivalent to solving approximate SVP, but there's this annoying technical detail, which is actually super relevant, which is that somehow the approximation factors are different. So it could still be the case that breaking lattice crypto is easy, solving gamma sec SVP is easy, but gamma SVP is hard. Or maybe exact SVP is hard, but gamma SVP is easy, right? So like sort of the hardness can break at sort of any one of these steps. And we don't know, we think it breaks at none of the steps, but we don't know. Okay. There's another reduction that's relevant here, just to make things more confusing, which is that we know that gamma SVP for some approximation factor gamma hard is hard. It's NP hard, which means in terms of reduction, there's a reduction from an NP hard problem like satisfiability or something to gamma hard SVP. This was a breakthrough result of ITAI. It was an open problem for 2 decades before he solved it. Actually, ITAI solved it for gamma equals 1, and there's been like a huge amount of work making this gamma hard as large as possible, so proving hardness for larger and larger approximation factors. But we're still in the regime where like all 3 approximation factors that I'm mentioning are different, you know? So you don't need to know anything about lattices. You don't need to understand like any of this talk to believe that some problem that I'm calling gamma hard SVP is hard. As long as you think P doesn't equal NP, then, or BPP doesn't equal NP, but who cares? Then you agree with me on this point. But it still could be the case that breaking lattice crypto is easy, or it could be the case that breaking lattice crypto is hard, but these worst case to average case reductions tell us nothing, right? There's a lot of ambiguity here. Still though, we have this sort of complicated but intimate relationship between lattice crypto and SVP. And I think like in aggregate, this provides a lot of evidence for security. The way that I think about it sort of succinctly is there's this dial that you turn. The dial is called the approximation factor, it's gamma. And we know that when that dial is not turned up too much, the problem is provably hard. We also know that the best way we know how to solve the problem for any approximation factor is to reduce to the hard case. So this proves that like all our algorithmic techniques, which go through the exact problem, can't be efficient. We need totally new techniques to do better. That's why I think this reduction is so interesting from this perspective. And we've got this sort of sandwich here where like we know that lattice crypto is somehow equivalent to solving approximate SVP, but there's just a little difference in the approximation factors. And the reigning assumption is that basically the problem becomes no easier between all these factors, or it becomes easier by a relatively small amount. There's a polynomial change in the running time. Okay, that's evidence for security. But here, evidence for not security, reasons to be worried. And I should say, like, look, my job security depends on the assumption that lattice crypto is at least interesting to study. So I'm going to be playing the devil's advocate now and arguing that like lattice crypto is not as good as maybe we think it is, but I am in fact playing devil's advocate. So like, you know, don't shoot me. So the first reason to be worried, I've kind of already said, which is that it could be the case that all this evidence for security could be completely vacuous, right? Like it could be the case that, okay, we're reducing from this problem to lattice crypto, but this problem's easy, so who cares, right? That's because all these approximation factors are different, so they're different problems. And in fact, like we kind of know that we'll never fix this problem. We know that we can't prove hardness of gamma sec SVP, or we don't know that because we don't know anything about complexity theory. But if we were to prove hardness of gamma sec SVP, then the polynomial hierarchy would collapse and complexity theorists would lose a lot of fun complexity classes to study. So we don't go down that route because we don't want to upset anybody. So we don't expect to prove that. More importantly, I've been using this word hard super vaguely, right? I've been saying, okay, lattice crypto might be hard to break. And like, what do I mean by hard? What I mean, or what I've meant so far, is no adversary running in polynomial time can break our scheme as n goes to infinity. this is an asymptotic definition, right? And as a theorist, this is what I'm comfortable with. You know, I teach an entire class where I pretend that this definition is reasonable, right? But of course, this definition is completely unreasonable from a practitioner's perspective. What does a practitioner want? A practitioner wants, well, I fix n and like say n equals 1,000, just a nice round number. And I want to say that for that fixed n, no adversary running in time exactly 2 to the 128, where like, what do I mean by time 2 to the 128? I mean, like you've got some processor and like it makes 2 to the 128, like, I don't know, whatever a bus is, you know, like 2 to the 128 bit operations. I'm not a practitioner. That's what we actually want to prove. And these statements are worlds apart, right? The question is like, how do we provide any evidence for the second statement, even if we're very confident about the first statement, and I am? How do we prove anything about the second statement? How do we get anything that suggests that it might possibly be true? And I should say, like, if you're a theorist, your answer might be we don't care, right? Like, okay, practitioners use n equals 1,000. Maybe they're wrong. You know, maybe they should take n equals 2,000 or n equals 1,000,000 or who cares? N equals 1,000,000,000, right? Whatever. But it turns out, and I'm not a practitioner, so like this still kind of blows my mind, that like practitioners care about factors of 2. So like we're willing to run the internet on lattice-based crypto with, okay, it's not exactly true, but for the purposes of talk, let's say n equals 1,000. We're not willing to run the internet on n equals 2,000. We're just like literally not willing to do that. We'll accept quantum computers breaking our schemes before we'll do that, because the efficiency loss is too large from a practitioner's perspective. So like we really need to nail this down. We can't just take n to be gigantic. And of course, even if n's 1,000,000,000, maybe the problem's easy. Like we have no idea. Probably not, but maybe. And like you know, I'm not the one who observed this. The people who really observed this are the people who are proposing lattice-based cryptographic schemes. So in particular, like these are 2 of the candidates for the NIST competition. Actually, Frodo's no longer in the competition, but New Hope is, but whatever, it doesn't matter. And these intentionally blurry graphics, so you don't look at them too closely, are tables in which the authors of these papers explain that they think that when you set n to some specific value and you set all other kinds of parameters that I haven't even defined to some other values, then they think that like the best quantum algorithm, the best plausible algorithm to break this scheme runs in time 2 to the 125. That's what they're saying here, 2 to the 125, and here 2 to the 128. So like super concrete, like these are the numbers exactly. And you can ask like, where did they get these numbers from? And here's the answer. Here's the answer. They assume that there's going to be no further algorithmic progress. So they assume that our current best algorithms for these problems are going to be the best. That's not exactly true. They allow for like a little bit of wiggle room, but the wiggle room's in like the ones digit of like the 128. It's a small amount of wiggle room. So I mean, that might seem like a reasonable assumption. In fact, I think it is a reasonable assumption, but here's a way to make it look really unreasonable, is just to list the recent algorithmic progress on these problems. So I know, I'm sorry, like if you're an expert in the audience, like Sasha, you realize, okay, like I didn't include everything. I'm sorry. There's a lot more recent algorithmic progress than just this. But is in fact the case that this is a very active area of research, which is really good for me. It's been a lot of fun, but makes the assumption that there's going to be no algorithmic progress really scary, right? In fact, like I'm being intentionally misleading here and making it look like I falsified this assumption that there's going to be no further algorithmic progress. Of course, I haven't. I'd be giving a very different talk if the algorithms that I'm listing here had actually broken these schemes. All of this progress has, for some reason or another, doesn't actually apply. For the most part, actually, the distinction is that the security estimates that are used to assess these schemes are based on heuristic algorithms. So they're algorithms that aren't proven to be correct, but seem to work in practice. And of course, if you're a cryptographer, like you can't just ignore such schemes and say, well, until you give me a proof, I won't accept that you broke my scheme, right? If the scheme's broken, the scheme's broken. You don't need to prove it. And most of this progress has been on provable algorithms, which are a bit slower. And then some of it's on problems that are closely related, but not exactly the same. The security estimates haven't been falsified. I actually believe them. But has been a lot of progress. Like, we don't know everything we could know about these problems, like not even close. It's a super fruitful area of research. And this is, just with a, workshop-sized group of people working on things. You'll notice a lot of these letters repeat a lot because it's a relatively small community. And nobody expects it to stop anytime soon. At least I don't. Okay. And while our evidence for security in this sort of polynomial time definition is very weak, our evidence for quantitative security is very strong. Sorry, our evidence for quantitative security is super weak. In particular, like, we have these reductions where we show that breaking lattice crypto is at least as hard as breaking some worst case variant of SVP, and we show that some worst case variant of SVP is NP hard. But if you actually plug in the numbers to these reductions and say, like, how large of a NP hard problem do I solve if I break SVP in the dimensions that we care about, the answer you get is like trivial. It's like a sad instance of size like 20 or something, which is solvable, right? Super efficiently. So like, these reductions for concrete numbers actually tell you essentially nothing. And like, this is not like this like idle paranoid theoretical concern. Well, maybe you think it is, but people have been wrong about this stuff before. In particular, the original RSA implementation from the 70s was broken in 1999. And it wasn't broken because of Moore's law. Like, when we're talking about like security of like 2 to the 128 or 2 to the 256, Moore's law, which is super powerful, is completely irrelevant. It shaves off some numbers in the ones digit. Doesn't matter at all. The original RSA implementation, if I remember correctly, Ravesh, Shamir, and Edelman estimated that it would take 10 quadrillion years. I might be off on that, maybe off by a few factors of 1,000, but something like this to break, and like, not just with like my laptop, they meant with like an Earth-sized computer or something absurd like this. And they were off by a few orders of magnitude. It took 25 years, which is not actually a negative. It's actually a huge positive. As Ravesh said, and when he won the Turing Award for this, he pointed out that like RSA encouraged people to study factoring. People then did study factoring. They found faster algorithms, and by the time that we actually like had an internet that was relying on this stuff, people like saw the writing on the wall, and key sizes were increased, and like nobody, as far as I know, nobody's security or privacy was violated because of this. And I should say, like, this wasn't because of a polynomial time algorithm being discovered. So it wasn't because like of like the analog here would be like falsifying p equals np or something like that. It was just a faster exponential time algorithm, which somehow all the reductions I show you don't tell us anything about. In fact, like, it was a change from like 2 to the n to 2 to the square root n, and then later to 2 to the cube root n. Okay. So in how do I want to manage time here? So in my last like 5 minutes, let me sort of race through the baby steps that we've been taking to try to actually prove some sort of quantitative security. The way that we do this is via fine-grained reductions. So a fine-grained reduction, which is kind of a hot topic in complexity theory right now, instead of saying if A reduces to B, then if A is hard, then B is hard, we get like super specific about the parameters. We say if A with input size n reduces to B with input size 2n, then if A is 2 to the n hard, then B is 2 to the n over 2 hard. So we like really care about the details. And this is the kind of tool that we're going to need if we want to prove, or if we want to get any evidence for like the kind of concrete security claims that practitioners actually need. And so like sort of the recent line of work that like I've been obsessed with, and Sasha's been maybe less obsessed with, but just as helpful on, has been showing fine-grained hardness of lattice problems. So in particular, like, we know that SVP is solvable in exponential time, and recently we've shown that it's not solvable in sub-exponential time. So for some pathetically small epsilon, we know that there's no 2 to the epsilon n time algorithm for SVP under some widely believed conjecture. And this even holds for small approximation factors. Since there's some evidence that like we're not in the entirely wrong ballpark. You know, like for RSA, they went from 2 to the n to 2 to the square root n. And like we don't expect the same thing to happen for SVP, but we could still go from 2 to the n to 2 to the n over 100, which would be just as devastating. And we've proved stronger hardness results for closely related problems. We have tight bounds for coding problems, nearly tight bounds for a variant called CVP with an asterisk because it's not exactly true. And we've proved strong lower bounds for SVP in different norms. So these are just technical details. I don't expect you to understand them. So let me finish just by telling you my dream. So my ridiculous dream is to prove the following theorem. This is not a theorem. It's not proven. It's some specific public key encryption scheme with some specific parameters cannot be broken into the 128th time. That would be great, right? Then there's this line, I think is it due to Silvio Macaulay, that cryptographers don't sleep at night, right? If this were proven, then cryptographers would be able to get some rest finally. My slightly less ridiculous dream would be to do something analogous to that with a sort of concrete path. So like these fine-grained hardness results that we proved, there are reductions from some hard problem to exact SVP. And we know that approximate SVP reduces to exact SVP in lower dimensions, and lattice crypto reduces to approximate SVP. And what I'd like to do is climb the ladder. I'd like to go backwards. I'd like to say, well, exact SVP in low dimensions reduces to approximate SVP in high dimensions, and approximate SVP in high dimensions reduces to lattice crypto. And this isn't too ridiculous if you squint, because we actually have versions of all of these reductions that already exist, but none of them are anywhere close to tight. And so like my dream is to make all of these steps tight. Even this almost certainly won't happen in my lifetime. But this approximation factor gives us a dial that we can turn. So we can prove some versions of these theorems, even without getting to my slightly less ridiculous dream that I don't expect to get to. So, you know, it's something to keep me busy, I think. Okay, so let me just summarize. Lattice crypto is coming. We'd like to understand it as well as possible, as quickly as possible, in particular before we bet the security of the entire global economy on this. We have pretty strong evidence for the asymptotic security of this, worst case to average case reductions, hardness of SVP, but we have very, very little evidence for quantitative security. And I personally feel a sort of sense of urgency that we should try to understand this as well as we can now. It'll be very embarrassing if we don't understand it now, and then 10 years from now, we figure some stuff out, especially if that stuff turns out to break the internet. Okay, so that's all I want to say. Thank you very much for your attention. I think I'm out of time.